Welcome to the Writing PDE Solvers talk. What I'm trying to do here is show you the interface that's underneath of NDSolve and how you can address that and use that and to write your own PDE solvers if you're so inclined. So it's a bit of an advanced topic probably, but I think still it's interesting to see how NDSolve works under the hood. Okay, so as we saw yesterday, solving PDEs takes a few things. You need to specify a region, PDE, and boundary conditions. Solve and visualize, that's generally the steps you need to take to do to address a PDE. And you will see that within NDSolve, the steps that I present here are probably, they're pretty similar. So just for a quick recap, to see how that actually looks like within NDSolve, so I've specified a rectangle. The PDE is a Laplacian. One thing maybe to note a bit is that for the PDE, so this coefficient here is -1 and -1/2. Just we'll see those a bit later. And then I've two Dirichlet boundary condition. So the rectangle is from 0, 0 to 5, 1, so it's rather longer than high. And there's two Dirichlet conditions, one on x equals 0, so the left-hand side, and another one on x equals 5 on the right-hand side. And if we solve that, we call NDSolve value PDE equals to 0, boundary conditions, the dependent variable u, x and y is component of the region, omega, which is a rectangle, and then we use plot for something to visualize this PDE. So this is the standard way how NDSolve works, and you can do a lot with that already. So I don't. The talk is over. So that's what NDSolve does. What I'm going to do now is try to show a bit how that stuff actually works inside. So the first question is a bit why do we have an interface at all? I mean, one important point is actually to make it understandable what is happening within NDSolve. I think NDSolve is probably one of the largest functions within Mathematica, code-wise and complexity-wise. It's good to be able to understand what's going on inside. That interface is used to make it possible for you to extend NDSolve, and I use this same interface if I write prototypes for new versions of NDSolve. So this is exactly the same thing I would do, and you can also do that. So if you're so inclined. Another important point is that the process of NDSolve solving PDEs is interceptable. What I mean by that is that if you are interested in getting out the system matrices or the element matrices or any detailed component of the process of solving the PDEs, you can do that. But for that, you'd need to use this interface. So NDSolve has components, basically 3 steps. And if you note, there's a tick here, and that's on purpose. So if you write NDSolve tick process equations, NDSolve tick iterate, and NDSolve process solution, we will see that in an example just now. That's the 3 steps that NDSolve takes to solve equations. Every equation is solved that way. What I'm going to do now is I'm going to pick out the finite element part of that. So within this process equations, we specify the region, we specify the PDE, and the boundary conditions. The iterate step will then call the appropriate solver. That might be a linear solve for a stationary problem, or it might be maybe a DIE solver to solve a DIE problem. And the process solution step will then in the end create the interpolating function that NDSolve returns and does some other bookkeeping. So let's look a bit at how that looks like. So the same equation we had before with the NDSolve value, I've now called NDSolve process equations, same argument, and that returns me something that we call the NDSolve state object. And that state object is an entire representation of the contents of the NDSolve solution process. I then give this process to and the state object to NDSolve iterate, and NDSolve process solution will then produce or return the interpolating function. So this is basically NDSolve broken up into 3 steps. And that's documented. You can look at the advanced documentation that shows how to do that. Right. So the first part is now we're going to look at this process equations step. That's probably the most complicated part of what we're going to talk about today. And then later we're going to also look at the iterate and the process solution component of this. OK. So if we now take this NDSolve process equation, that returns this NDSolve state object. And within this NDSolve state object, there is a finite element data object embedded. And this finite element data object contains all the data that has been processed from these equations. Now, right. So, OK, now the first thing maybe to note here is that you can, in principle, use NDSolve process as an equation processor. So if you are a commercial or even academic, doesn't matter. If you're a person that would like to write their own solver, you can use NDSolve as an equation processor. So you can write the PDEs or ODEs, what you have, in a normal form and extract them from NDSolve and then feed them to your solver. So that would allow you, for example, to write your own PDE solver with a nice differential equation interface. So you could do something like that, just as a first thought. OK. So this process equations, that does a few things. So the first thing that is done is basically variable data and solution data are set up. Variable data is the symbolic representation of the problem, so to speak. So it will have the dependent variables, x and y. It will have a notion about the region. And the solution data will have exactly the same components as the variable data, but as a numerical counterpart, so to speak. And we'll see an example of that. Then for the PDE, there is the function called initialize PDE coefficients. For the boundary conditions, we call the function initialize boundary conditions. And then again, for the proper initialization, we call initialize PDE method data. And that will initialize the finite element method. That sounds a bit complicated, and I think I should have an example, right? So what we do now is the same equation we had before. We're going to write this in a really manual way. So what I do now is, so NDSolve variable data, the dependent variable and space component. So the dependent variable is u. That's the same equation dependency we had before. X and y is the independent variables of this equation. From the region, this rectangle, we create a numerical region and set that to the solution data. So you see the correspondence here. Space is the x and y component, and space here is the numerical region. So this x and y is component of this numerical region omega. So that's how they correspond, these two. And the reason we don't have a dependent variable setting here is just the fact because that dependent variable is actually the solution we're looking for. We don't know that yet. That's going to be populated at a later stage. OK. The initialized PDE coefficients gets these variable data and the solution data, and then you specify the coefficients. Diffusion coefficient is the identity matrix minus, and the load coefficient was -0.5. So these are the corresponding coefficients of the PDE equation we saw before. That generates a PDE coefficient data structure. And we initialize the boundary conditions in exactly the same way. Variable data, solution data, and the boundary conditions we specified before. And that returns a boundary condition data. OK, so, right. And the last part, we need to initialize the PDE method data. OK, so these three components are done. And if we look again now at the NDSolve process equations, the example I showed 2 slides before, this is the equation which returns the NDSolve state object, the finite element data. And if you look at the properties of this finite element data object, it has the boundary condition data, the finite element method data, the PDE coefficient data, properties, and solutions. And the first 3 are exactly the ones we've just generated on a manual way with calling initialize boundary conditions, initialize PDE coefficients. So you can actually, you don't have to go through that. You just use this process equation, and that will generate these data structures for you. I just wanted to show you how you can actually even manually generate them, and we'll probably see an example of that a bit later. Right, so we now have, we extract these data. The PDE coefficient data is just extracted with a string property, boundary condition data, and method data. So PDE data, boundary condition data, and method data are extracted now from this NDSolve state object. Right, and that's the point I've mentioned earlier. So in principle, you can use NDSolve as an equation processor if you want to do something like that. OK, now we go to the second state, the iterate state, where we'll try to find the solution of this particular PDE. And for that, we have two functions, discretize PDE and discretize boundary conditions. The discretize PDE gets the PDE data, the method data, and the solution data, and that will return the discretized PDE. So this process, this is actually the function that does the real work. And the same, we have that for discretized boundary conditions that will return the discretized boundary conditions. In the next step, you extract the system matrices, so the load matrix, the stiffness matrix, damping, and mass matrix, if you have these. You see that there's like 1,300 elements. It's a vector. And this is 20,000, roughly 20,000 components, and 1,300 by 1,300. Now, you need to combine the boundary conditions with a solution, or with a system matrix, and that's what the function deploy boundary condition does. So the system matrices here are now modified with these boundary condition data that we computed before. Then we call linear solve. That gives us a result. And now we proceed to the next process in the solution stage. That will generate the interpolating function. And there is the function element mesh interpolation, extracts the mesh, and the result we computed with linear solve. And then we can plot this. So this is how, now you've seen all the steps, the basic steps that NDSolve takes internally to solve a PDE, a stationary PDE. OK. So here's a summary of all those slides. There's lots of stuff on the slides, but if we quickly walk through that again. So call NDSolve process equation with the equations, the boundary conditions, the dependent variable, and the specification of the region. We extract the solution data. We extract the finite element data, the coefficient data, the boundary condition data. Here's the method data. And this function returns the discretized PDE, the discretized boundary conditions, solution data, and the method data. So a basic application example or basic usage example would be PDE to matrix. So that will return me, as an argument, I'll give the PDE, the boundary conditions, and it will return me all these four data components. And now we're going to do a little bit with that to see how that's actually useful. So yesterday, I showed ND Eigen system, which is a new function coming up. And in principle, you can write it with exactly the code I've shown now. So we use this function PDE to matrix. So here's a time-dependent PDE, du dt, Laplacian, an initial condition, the dependent variable, t from 0 to 1, x and y of the component of omega. And that returns the discretized PDE, the discretized boundary conditions, the solution data, and the method data. Now, we extract the system, the stiffness matrix, and the damping matrix, and we call eigensystem, not ND eigensystem, but eigensystem on these stiffness matrix and get the smallest four eigenvalues, and these are the four values it returns. And this is exactly the same result as what ND eigensystem gives you. So basically, this small function here that I've written here is basically the core of what ND eigensystem does. It's not, obviously there is more code inside it to check for wrong arguments and verifications and constructions of solution. That takes quite a bit of code as well. But the core concept of ND eigensystem is basically this. So it's not that much. I mean, it's doable, I think. So, OK. I mean, you could have other stuff. You could have ND singular value decomposition. I mean, why not? I don't immediately see what an application for that might be, but you could do that. I mean, why not? ND singular value decomposition. That would be exactly the same code. And when you start thinking about it, well, you can take this even further. I mean, you can have basically all of the linear algebra functions that Mathematica offers and discretize the PDE, make them to system matrices, and then have an ND least squares, matrix-based minimization, ND, whatever decomposition could be implemented with that. So that's the basic framework for that. You want to take a guess how how n integrate with the finite element method works? It's exactly the same thing. It's exactly the same thing. This is not a secret. This is how the finite element method works. You take a PDE, you generate a discretization out of it, and then you can apply linear algebra to it. OK. Now, here's another example I wanted to show. Say you want to implement a new type of a boundary condition that we don't currently support or don't have. So what you do now, so here's the application. So we have a Laplace equation, and you have a Neumann value, sinus xy, blah, blah. It's not that important, actually. So NDSolve rightly complains about this and tells you there's no Dirichlet condition or no Robin type. So here's no dependent variable involvement. So no Dirichlet or no Robin type boundary condition was specified, and the result may be off by a constant value. That means this result that we get here, it's correct, but it's floating. It could be lifted up or lifted down on the solution. So it's not a fixed solution. So we want to now write a boundary condition, and here what I've done is I've integrated over the solution, and it gives me the value of minus 18 something. So it's an arbitrary value, basically. It could be anything. Now we want to write a boundary condition that actually allows us to say this integral should be a specific value. I want to have a boundary condition that says this integral should be, I don't know, 43. I think that's what I chose. So let's do that. OK. So I use this function PDE to matrix, Neumann value, exactly the same as I entered into NDSolve. It complains in exactly the same way, but now we just ignore that. We don't care. We extract the load vector, the stiffness matrix, and deploy the boundary conditions, the ones that are present. So this one is now deployed. It's in the system matrices. We extract the mesh, the degrees of freedom, and then I've written a small function, make integral constraint. I specified I want this integral constraint to have the number 43. I give some data is transferred, and that returns me a discretized boundary condition data again. Now, what's happening inside here? It's not that important. It's not really the point. The point I'm trying to make is that you actually can write your own functionality to extend this. We deploy this boundary condition, call linear solve, make an interpolating function of it, and voila, we have an integral that now roughly is about 43. Now the integral of this area is now about roughly 43, which we wanted. So this is just another way to extend the functionality, if you're so inclined. Transient PDEs. So here I have, OK, so this comes from a chemical application. You see the red dots here, that's where a voltage is applied, and the blue part is where another voltage is applied, and you try to measure the voltage across this object. The application is not that important. So we have a mesh. We generate a mesh out of that, and this has about 2,500 degrees of freedom. That's going to be important in just a second. I call the function PDE to matrix. It's a transient problem in 3D. I specify some Dirichlet conditions, and as usual, I get the discretized PDEs, the discretized boundary condition, solution data, and method data. And I extract these system matrices, deploy the boundary conditions, and then what I do is I use NDSolve as a time integrator, as a pure time integrator. So this is the discretized damping matrix, the discretized stiffness matrix, and the load vector. So this is basically what NDSolve with the method of line does. So you take the PDE, convert it to a system of ODEs, and then NDSolve does this time integration. So that's roughly how that works. Now, for this specific example, this took about 21 seconds to time integrate. OK, fair enough. But now I decided, OK, and this is the solution. It's not pictures. It's OK. But now I want to do something else. So we have the system of equations. That's 2,000 equations. Can we find an equal system that is much, much smaller, but has the same properties? And yes, the answer is you can do something like that. That's something that you do with model order reduction. I don't want to spend too much time on how that actually works. But basically, again, the input is the system matrices. They're mangled around, and something magically, a system comes out that is much, much smaller but has similar properties. So I've written this small model order reduction code. I've done the model order reduction, which takes 0.2 seconds. And this produced me system matrix load, stiffness, and damping that are on the size of 50 and not 2,500. And I can then go ahead and plug that into NDSolve as a in the time integration step. And that then, of course, is much, much faster than the version before. So this is a way to speed up time integration things. That's another thing you could do with that. And here's a small plot that the solution is, I mean, roughly is okay. It's not, I mean, it's not super. You could use more than 50 control points, I guess. But this is, I think it's fair enough for such a small system. So that's another idea. OK. All of what I've been talking, this is a lot of material, I understand that, and it's not entirely trivial, I understand that too, but all of this is documented. So initialized PDE coefficients, it's documented what it takes as arguments, what it returns. Right, there's an entire tutorial about finite element programming. It's a long tutorial that explains how to use these concepts that I've tried to show here. Another thing that may be important is the finite element method guide. So that's a starting point where you can dive into the finite element method on various levels, so to speak. Yeah, thank you. But stop. Nonlinear PDEs. It came up yesterday, so I took up the challenge. I wanted to show this today. So if you want to solve nonlinear PDEs with this, it's a bit hard, but you can do it. So there's two things you need to do to solve nonlinear problems. The first thing is you need to linearize the nonlinear problem. You need a linearization point. I'm not going to go too much into detail how to do that. But what I'm going to show is how you actually would, how that would work in principle. So the idea is basically the coefficients of the PDE can be any function. So what we do, at a certain point in the nonlinear iteration, we extract the data and create an interpolating function of the dependent variable and reinsert that into the PDE coefficients. That's the idea how to do that. It's not going to be terribly efficient, but it's a way to prototype it, I think. So I've done that. So, and because fluid dynamics came up, we want to go full throttle. So we go Navier-Stokes equation. What I have here is a region, and we're going to have kind of an inflow, and there's a hole inside, and we want to see how the stationary solution for this Navier-Stokes problem looks like. So here's the boundary condition. I set the pressure to 0 on the outflow. Here's an inflow boundary condition here. That's how fast the fluid flows in. And the rest here is that all other components have 0 velocity. So here's no velocity, and on the edges, there's no velocity. So, what I've done now is I've separated the nonlinear and the linear component of the PDE. So the first thing we do is we solve Stokes' equation. I've put that into the PDE2 matrix. That gives me the load vector, the stiffness matrix, variable data, method data, and the components. And then I've written a small function right-hand side. So the first thing it does, it interpolates over the mesh the different components, the velocity vectors, u, v, and p. So that generates a p0, u0, v0. And then this is a do loop. In this do loop, I reinitialize the PDE coefficients. And there you see, for example, v0, u0, here's another u0, a p0. All right, and I rediscretize the nonlinear components, extract the nonlinear parts, add them to the linear parts, redeploy the boundary conditions, use linear solve, increment the old du plus the new one, and then I do this 8 times in the hope that it has converged after 8 iterations, and it's I think it's a bit crude, so I put in a print statement. So here, the first residual is 0.3, the correction is 0.38, and you see about here, that's where really the nonlinear fun begins. So we have 4 zeros, and it's going down to 10, and then basically in about 6 iterations, we've broken the problem down. And so these are then the the solution, this is the u velocity component, the v velocity component, and the pressure component. One thing I must admit, I mean, it's not, I mean, I just choose this because I had some code of this lying around. It doesn't make that much sense to compute a stationary solution for the Navier-Stokes equation. I admit that, but it's just, I wanted to give this proof of concept that you can write even something like that. And that's pretty sophisticated, I think. So, and I think we need to go back. So, NDSolve rocks, as usual. Thanks for your attention. Yeah.